Guten Tag und willkommen alles. Tachahau. Salam sejahtera semua pada para hadirin dan hadirat sekalian. Hello, good afternoon. My name is Larissa Zimera, and I'm from Rockflow Dynamics Kuala Lumpur. And we would like to thank you for joining us today for our third session of tNavigator Podcast 2020. This podcast session will approximately take around 45 minutes. And there's going to be 30 minutes of discussion and 50 minutes of Q&A. And before we begin, I would like to brief through some points to all of our attendees on how to navigate yourself during the session. So before you dive into the podcast, all of you will be automatically muted. And if you have any questions or inquiries, feel free to drop them into the right panel that is on the right side, the control panel on the right side of your webinar. And if you have any questions or inquiries, and if you're interested in a tNavigator demo, feel free to reach us at asktnav@rfdyn.com. That is at asktnav@rfdyn.com. So in today's session, we have a few moderators joining in from Kuala Lumpur. On my left side, we have Mr. Ari Krishna. Would you like to tell us a bit about yourself?
Sure, Larissa, thank you. Hi guys, my name is Ari Krishna. I'm the senior geologist based in Kuala Lumpur here for Rockflow Dynamics. I'm also taking care of the podcast here and also previous webinars. So yeah, very good opportunity to join you, Larissa, here for the podcast.
Yeah, it's something very different compared to our usual webinars. We're trying to make it as interactive, and we would like to have most of our participants come onto this platform and share their knowledge and engage with us even further. So we have also on the other side of the line, we are broadcasting live from Indonesia, Jakarta, Indonesia. We have Mr. Rizkiaputra. Hello, hi. Would you like to tell us, Mr. Rizky, how's everything on your side?
Hi everyone, I'm Rizky. I'm Reservoir Engineer from Reservoir Dynamics Indonesia and based in Jakarta. So actually, this is my first time become a podcaster. So let's see how will I perform. So if it turns out to be okay, so maybe I will consider to be a YouTuber instead. No, it's nowadays YouTuber sounds promising, right?
Perfect. Okay, let's just hope everything goes well. Okay, so on the other side, we have our very special guest speaker from Medco E&P Indonesia. Hi, Mr. Ricko Rizkiaputra. Would you like to tell us a bit about yourself?
Hi, Larissa. Hi, Mas Ari, and hi, Mas Rezi. Good afternoon. It's been a pleasure invited by tNavigator to share my project in here in Medco E&P. This project has been worked with engineers of RFD in Jakarta as well, so hope that this topic is interesting and get some insight from our project.
Perfect. Sweet. Okay, so the topic that we're going to be discussing today is the application of simplified model for post-acid fracturing well performance analysis by using grid connection. Mr.
That's
Ricko,
quite a mouthful, yeah?
Yeah.
Very long title.
I had to take one deep breath. Mr. Ricko, could you tell us why you have chosen this specific topic for this podcast?
Yeah, well, this topic has been an interest in my team, in my subsurface team, in my company, because we have done the acid fracturing job. You know, I've been blessed that my reservoir is tight. It's less than 0.1 millidarcy. So there's opportunity to frac it and to increase its deliverability. And after that, there's also a challenge to model the well performance post-acid fracturing. So with the help from the engineers of RFD from Jakarta, we try to solve that issue. So in here, we would like to share the application of simplified model that is available in tNavigator of using the grid virtual connection.
So I'm guessing you and Rizky work closely together?
Yeah. We are working these topics, I think, in late 2019 until early 2020. So it has been a few months of great collaboration between us in Medco and also RFD teams. So really glad that the project has been done, and get a positive impact for me and the subsurface team regarding the result.
Oh, that's
actually,
so good.
to be honest, I didn't
Okay,
really...
so shall we dive into it? Okay, the floor is all yours, Ricko.
Yeah, please go ahead. I'm going to give you the access so you can access the PowerPoint from Jakarta.
All right, thank you. So this is mainly the topics. So probably would like Mas Raji maybe would like to.
Yeah. So I slightly saw your presentation slide before we go here, and I really amazed that you want to discuss the topic about grid virtual connection, right? From your hydraulic fracturing job in Medco E&P. So I just wonder, is there any kind of simulation practice in the Medco E&P Indonesia rather than the hydraulic fracturing job?
Yeah, I think there's Medco has a lot of field like plastics and also carbonates. For my team that we manage carbonates, the tight one, the 0.1 millidarcy, less than 0.1 millidarcy of reservoir. So it has been a challenge in there. So yeah, we have been trying everything basically from acidizing, and also we assess the opportunity to sidetrack, and also another stuff, and then we end up with the fracturing, especially the acid fracturing. So that's the option that we would like to pursue, and it seems that in campaign back in 2019 this has been successful, and I think this one is the best case study for us to do the well modeling of the post acid fracturing. So I think that will be discussed in this session.
Okay, so I can see now that's why you talk with this discussion to the public. So how about the challenge? I mean, previously I know that there are three or several methods to simulate the hydraulic fracture in the reservoir, right? And I see that you already tried to simulate or to see the effect of skin factor, to effect of the local grid refinement, and also the virtual grid connection, actually special tool by tNavigator, right? So what do you think about those three tools?
Yeah, I think there is no right or wrong in each of these methods. So the objective itself that we would like to create a fracture model that of course closely mimic the physics of the fracture, and also we would like to quickly simulate and investigate the fracturing cases. That's the main objective of this project. However, we see the challenge that we use the conventional practice, such as using the skin factor or local grid refinement. In here, for the skin factor, I think it's too simple and it's too simplified to be applied in numerical simulation. Basically, when you have a very negative skin factor to account the increase of the deliverability of the wells, sometimes the numerical simulation could not handle it, because that's the physics of the numerical simulation itself that has threshold of negative skin factor that could be handled. But in the positive side, the skin factor is simple and it's quick to simulate. So, and the other side, there is also the local grid refinement, which closely mimic the actual fracture behavior. You can refine it anything from the X direction, Y direction, or Z direction. You can refine it with logarithmic or unstructured or something like that. But I think the negative sides is the complexity of the modeling of the fracture, and it will require high computational time. Especially this is it's problematic if you have the inputs of the fracture that is not as too detailed as the simulator has. But all in all, if you have the more detailed fracture models and something like that, you can always use the local grid refinement. But in my case, I don't have that luxury to have the detailed model of fracture from my fracture simulator. So in this case, to bridge the gap, I would like to proceed with the grid virtual connection that available in the tNavigator. So let's see what the function can do.
So I believe that you want to suggest or recommend to all the users, tNavigator users, to try the virtual grid connection, right? So I also know that you previously using the skin factor for your simulation before you know the virtual connection, right? So what do you think the best case or the best scenario to use this method? What condition of reservoir will be better to use it?
Okay, I think that's a good question. Some of my colleagues asking the same question to me. Well, I think the skin factor is suitable if you have like acidizing program where your reservoir exposure is limited, let's say like 10 feet or 20 feet, not too deep to the reservoir. But in his case, when you have a fracturing, you introduce a fracture planner and you penetrate, let's say like 100 meters or 150 meters, then you introduce a heterogeneity of the reservoir in there. So maybe the approximation using the skin factor model no longer valid. You need to use the more sophisticated approach, whether you can use the local grid refinement, which in this case like time consuming and also high computational time and require lots of inputs. But in this case, I use the grid virtual connection because the inputs from the grid virtual connection in here is suitable from the output from the factor simulator that I get from my job. So yeah, the approach of using the grid virtual connection in here, that will be deeply discussed in this session. So hopefully that it will be give you an insight regarding the method and also the result.
Yeah, that's true. I think I also saw several examples from my clients here in Indonesia. They have the fracture model using skin previously, right? But sometimes the skin is very high, and then it becomes not reasonable anymore. So that's why maybe these new methods kind of helpful for this kind of condition. And also, I see that you propose a solution for your study is using the grid virtual connection, right? So I wonder. Why wouldn't you use the local grid refinement idea? Because it's also the sophisticated tools nowadays.
Yeah, the grid the local grid refinement itself is quite sophisticated method, and it takes a lot of inputs detailed. You can use the fracture arithmetics and the fracture zone permeability and something like that. It's very fancy tools. I have no doubt in there. But in here, I have limited with the inputs from the fracture simulator, so that's why I use the grid virtual connection. And in here, I think in the solution that Tina has offered is quite comprehensive, because in the pre and post simulation, I can utilize the Streamline analysis to see whether the fracture itself can mimic the actual physics of the fracture, and also there is a LGR fracture model to compare the grid virtual connection with the local grid refinement and also a skin factor as well. And there's also the feature of history matching with assessed and uncertainty analysis. So we can calibrate the model using the experimental design, multiple objective function, and also multi-relation run. I think that's the very important thing, because where the inputs that we put in the simulator needs to be calibrated with the actual data. So this play a big role in my project.
Nice. And also about the grid virtual connection itself, I believe that you already know the physics behind, right? So are you sure about the numerical simulation, whether is it correct physically or not? I mean, how does it actually works in the simulation?
Well, I think specifically with the fracture, we can recall it with the flow behavior of the fracture to the wellbore, from the reservoir to the fracture to the wellbore. Well, we have a in PTA, the pressure tension analysis, we might see the bilinear flow of response. So that thing that we would like to dig in the simulation. If we use the skin factor, that kind of bilinear flow, we couldn't see it in the simulator, because that's basically only from the reservoir to the wellbore. And from the local grid refinement, we can see it clearly, because you have refined shells in there. And then there is a high permeability streaks when it comes to play with the reservoir and the fracture to the wellbore. And in here, the approximation using the grid virtual connection, I will show you the streamline result. It creates a nodes of the completion nodes outside the wellbore, the main wellbore, and it acts as another influx of the outer side of the wellbore. So it's still approximation, because the real physics is will down to the local grid refinement. But this grid virtual connection itself is quite there to mimic the fracture.
Nice. Okay. Also, I also surprised that you also use another tools called the HM and uncertainty model, right? So So what do you think? This to help you a lot, or what will you miss if you don't use this tool?
Yeah, I think this tool is amazing because at the end of the day, when you have the inputs, you need to calibrate it, and to perform the calibration, you need to the correct tools. In here, I use the assisted story matching. So the first is very powerful. You can quickly calibrate your fracture model in this case. So, and also if you have the match and you would like to proceed with another wells, to fraction other wells, and to see the outcomes of another well that need to be fracked, it can also be used to simulate the expected gain that will be obtained if you frack the other well. So that's two main options that I use in this project.
Okay, so I can see that maybe if you don't use this tool, you have to manually tune in the properties, right, into your
Correct.
fracture design. So maybe it took a longer time to get the best match, right, for this matching. Okay, okay. Now I really want to see what is the workflow of your project here, or if your study here. Are you trying to simulate all those three or only one? Okay, here you go.
Okay. So yeah, exactly. So the basic input itself is the reservoir model that we have, and also the acid fracturing model. So let me show you the highlighter in here. So we have the reservoir model, our fine reservoir model, and also the acid fracturing model from the simulator, fracture simulator. So basically we input all of this and we do the numerical simulation, and we assess all of the three methods from the skin method, skin factor, and grid virtual connection, and also the local grid refinement. With each of the method, we would like to see the simulation running within base input. So base input will be performed in each of the three methods. And also we would like to see whether the inputs can be reasonably matched or calibrated. So we perform the history matching in each of these methods. And at the end of the day, we need to QC of the results. So there is the steps in here that I do is a matching result QC. So all of these methods. And again, after we do the calibration of our models, we would like to proceed with the forecasting to find the gain of the projects, and also we would like to see the opportunity to frack the other wells. So this materialization forecasting will be helped to answer the question.
Okay, so just to make it clear, so previously you have the match model, the match natural flow model, right? And then you put all three methods into this model, and then you do another history matching for the production after the radioactive fracturing introduced. Is it correct?
Oh yeah, that's correct. So
Okay.
the model that is inputted in here has been matched until it's pre-frac. So all of the wells, all of the whether it's rate and also the pressure has been matched until at the time it needs to be fracked. And after the well is fracked, there's another what do you call it, the objective function or the matching point that we'd like to pursue in there.
Okay. Okay, I see. So, are you using the same input from the same hydraulic fracturing design? I mean, for all the three methods, because those three require different kind of inputs, right? Each of them.
Yeah. So let me show you the inputs. So this one is our reservoir model in here. So there is one culmination in eastern part and one culmination in western part. And what we are talking about is the wells in the eastern culmination part marks with X6, X8, and X7. But in this case, we would like to focusing on X6 and X8 because both wells are our main wells that we have been fracked. So this is the case study of this project. So regarding the reservoir properties itself, like I told you earlier, that we have we are blessed that we have such a wonderful reservoir in here. It's 0.03 millidarcy in average. Yeah, so it's quite a challenging reservoir, and the porosity itself is 3%, so it's nice. And the reservoir fluid, we have another nice thing in here. We have retrograde gas condensate, so it's quite challenging reservoir that we have in here, and it's quite over pressure. almost 7,000 psi of the pressure in there. But in here, we would like to focus on how to increase the deliverability. So there is a project of acid fracturing in here. So X6 and X8 has been fractured in 2019. So I will go through with the packs in here and show you how we calibrate the post acid fracturing well performance by using the grid virtual connection.
Just
can I have a quick
question? Sure. Yes.
Yes.
Yeah, I mean, because I'm a geologist, I always look on the scale of the. So what's the distance between the X6 to X8? How far it is between the two wells? Because I couldn't see the scale in the map. That's why I'm asking. Just
okay,
out of curiosity.
Sure. Okay, this reservoir is quite massive. So the distance between X6 and X8 is approximately like 3 kilometers.
Oh, okay.
So we have the line between this top culmination in western part and in eastern part is distance of like 20 kilometers. So it's quite a big reservoir in here. So that's why we have an interest to develop it a little bit further. And this kind of job, the fracturing job that has been successful, brings up the opportunity to perform the fracturing in another wells, another infill wells or something like that. So this project is important because you can models the post-frac performance in more details.
Okay, thanks.
Okay, so just before we go, I just wonder, did you manage to match all the three methods using this model?
For the local grid refinement and also the grid virtual connection, yes, because the inputs are complete. From the grid virtual connection, you can input exactly the output from the factor simulator, and also that applies to the local grid refinement because it's more detailed. And for the skin factor, unfortunately, no, because I have sensitivitized with the negative skin factor, a lot of negative skin factor in there, like until -10 or -20, just to check the match that been produced. But that cannot be matched. Why? Because I've read the manuals and also the physics and asked the colleagues in my office that the matching with the skin factor, it will be limited by the radius of investigation because you have the equation of skin in there with limited with the radius of investigation. So in this case, the simulator investigation is limited by the grid size. So that's the bounded by there. So when you have the actual number of the negative skin factor, it will check with the radius of investigation of its grid cells, whether it is reasonable or not reasonable. For reasonable, will be go ahead, but if it's not reasonable, it will chop and it will be set at default number that the simulator can handle. So that's the case with the negative skin factor. So in here, what I've been done from the skin factor, unfortunately, we cannot do matching in here. So I will proceed it with the local grid refinement and also the grid virtual connection.
Okay. I think you can proceed. But how long it took to match the models using the local grid refinement and the virtual connection roughly? Is it 1 week, 1 month, or 1 year just to get the match model?
That's an interesting question. I think it depends on each of the models that we are working with. But in my case, in this reservoir, it's not too long. I think the most important step is the setup of the inputs. Make sure that we have the correct inputs, and also make sure that all of the wells has the inputs that needs to be fit. But for the calibration itself, it helped by the history matching with assisted method. So it's quite fast. I think that the project itself is only 1 week for the matching itself. Yeah,
wow.
Because because it's not that hard to match with the grid virtual connection because you have the straightforward inputs. And the input itself has been defined in the factor simulator. So there is just no assumption in there, just straight from the output from the Spec simulator. So it's pretty much straightforward, and we have a reasonable reasonable result from there.
Oh, cool. I would like to see more about your study. Can you move on?
Yeah. Okay.
Wow.
For the start, I'm setting up the grid filter connection. That at the thing that I talked to you earlier. This is the most important things because you need to set up correctly your inputs in there. So in here there is 3 wells, X6, X8, and X7, which the main of interest is X6 and X8. So, and then if you see this, there's a completion data in here. Just to make sure that we have correct inputs regarding the completion data, I would like to proceed with the fracs. And this one is the frac option. You can select the manual, or you can select the automatic. Basically, automatic is that you have the propans or something like that. But in this case, I have all of this input that necessary to proceed with the grid filter connection, such as the azimuth and azimuth angle, fracture height, fracture length, and fracture conductivity. These inputs are ready in my frac simulator. So I proceed with this. This is the parameter that is extracted from the fracture simulator. So at the time step after the frac has been performed, this is the result. You can see there is a yellowish planar in here that shows you that the planar has been activated. So I will show you in more details in upcoming slides that shows that how the streamline result from the fracture planar from the reservoir to the nodes outside the wellbore and then nodes to the wellbore. So this kind of setup that we like to do. But remember, this number is the basis, the base number that exported from the fracture simulation, and this number needs to calibrate it with the actual production data of post-frac. So this one, that's our main interest to perform the calibration in here.
There is an announcement in my office. You can move on.
Okay. So I think I talked about a little bit about the streamline, and this is the result of the streamline. So you see in the tNavigator, you can mark the streamline based on each wells. So you have a streamline from X6, from streamline from X7, and streamline from X8 in here, marks with the brown color. So the total active grid cells in my case is around 240,000 grid cells, with the total time steps on 133. In this case, because my reservoir is retrograde gas condensate, I use the approximation of the black oil with the PVTG or condensate drop of the reservoir, and also I also model the oil in here. In my case, I have the 32 core of computer with the GPU assisted, so that might speed up my works because the tNavigator can do with multiprocessing. So this is the simulation keyword for virtual connection. So this is the basic inputs from the simulator that told you that we need to do frac at that particular time step. So this one is the pre-frac streamline. As you can see, the streamline is straight through the wellbore from the X8 and the X6. And after the streamline, after the frac has been performed, and you see in here the streamline itself, there is creating a nodes in here, a new intake from the X8 and X6. You see the streamline coming to the red dots in here. That shows you where the grid virtual connection is activated. And also this apply for the X6 as well. So this mimics the physics regarding from the reservoir to the wellbore, and the wellbore to the reservoir to the fracture, and fracture to the wellbore.
It's great, right? If you have the streamline to see the pressure connection into your reservoir and see where the flow coming from. And also, I really amazed with the simulation running time. It only took 2 minutes 25 seconds using the grid virtual connection, and I believe using the logarithmic rate refinement will took longer. Yeah. How much does it take for the LGR?
Okay, for the LGR, I think it's 5 times slower in here. It's around like 10 minutes. But again, 10 minutes is still, I think it's still reasonable for doing the simulation. But in this case, I don't have that luxury of the inputs that is offered by the local grid environment. It's grid tools, but I don't have the luxury to provide the necessary inputs, such as the actual simulated reservoir volume and also the arithmetics and something like that. It needs a lot of assumption in there, but I don't want to put a lot of assumption in there, because my only inputs is only down to the height, length, and width of my fracture. That's basically the essential fracture output from the fracture simulator. So that's why the grid virtual connection is quite really nice tools in here to perform the fracture simulation. But another thing regarding the simulation learning time, I've compared it with the skin factor as well, and it's the same. So the skin factor is around 2 minutes something. So it's on par with the skin factor method. So it's quite fast regarding this approximation.
So if you have the limit and the constraint in the time limit, or also maybe in the data information availability, so maybe the grid virtual connection will be best, yeah. But if you maybe have the privilege in the more detailed data and then more time to do the studies, so maybe I think the LGR will be also good to consider, yeah. Because I know that there is another tool called the SRV LGR. So you basically model the secondary frac as well, rather than only the frac body. So I think that's gonna be a big a huge loop if you want to use it later on, maybe.
Yeah, sure. I think for the grid virtual connection, it's suitable for you to have like a preliminary simulation for if you apply the fracturing job in your field, to see the quick assess the gain of doing the fracturing. I think this is the best tool to do that. Before you jump into the more details with the SRV LGR, it will be you have your more data and also more inputs in there, so you can proceed with the SRV LGR.
Yeah.
Ricko.
Nice.
Hi, sorry to trouble you. So one of our users are asking, attendees, he's asking, what is the grid size?
Okay, so in my case, the grid size is 100 by 100 meters with the in the X and Y direction. For the Z direction, for vertical thickness is roughly average like 4 meters.
Okay. Hope that answers the question. You may move on. Carry on.
Okay. So later on, we have talking about Mas Rezi talk about the calibration, right? In here there is the brief calibration process. So we have the experimental design in here from grid virtual connection. So basically the inputs is the same as the output from the fracture simulator. We have the base case and minimum case or maximum case. We can also put the distribution in here. You can use the uniform or logarithmics or normal or log normal or triangular, something like that for the distribution. And also you see this, the experimental design. So the experimental design, I think, is the great tools to capture to make sure that the inputs that you have in here already capture the data. If you see in here, I'm not sure if okay, I can zoom in. Okay, so the matching point in here will be the gas rate constraint. Sorry, the constraint in here will be the gas rate constraint, and the matching point will be the bottom hole pressure. So as I talked to you earlier, we take as it is from the simulator. So we take from the pre-frac, and we proceed with the post-frac to match the result of the post-frac data. From the inputs that we have been done, and we set the minimum and maximum, you see it already capture the data, the bottom hole pressure, meaning that the inputs in here, the length, width, connectivity, and so on, from the min and maximum side, has already captured the data whether it's X6 or X8. So, and this one will show you regarding the tornado diagram to show the most affecting parameter in here for length, width, conductivity, and proper height. That's the most affecting parameter. Meanwhile, the azimuth in here is not really affecting the job. So we can take this parameter to go forward from the optimization, because in here it's only from this first screening out to see whether our inputs are already captured data and which data that is most affecting our simulation result.
Azimuth is not really sensitive in this model, yeah, in this history matching process. But I don't know. What do you think? Is it what is the reason behind it?
I think that's the nice question, because in here the azimuth is dictated by the geomechanics. Unfortunately, in our field we have the geomechanics, and we can see the trend of the fracture. So pretty much is given. So I could not play any direction I wish, because it dictates with the stresses, horizontal stresses in my reservoir. So pretty much that's close. So this azimuth, we can exclude it for the optimization, because in here that's showing not to really any significance regarding the output of the result of the simulation.
I see. And then you move on to the optimization, I think. Is it correct?
Oh yeah, sure. For the optimization, so firstly, you can set up the objective function. So as I told you earlier, the matching point will be the bottom hole pressure, because I set the constraint of the gas rate. So the bottom hole pressure of the X6 and X8 will be the objective function. In here, I have also blessed that my field has the bottom hole gauge, so downhole gauge. So it's a real time, so I can retrieve the data daily. So yeah, so it reduces the uncertainty of the matching. So I use the bottom hole pressure as the matching point in here. So the first one is you setting up the optimization algorithm. You can use it anything that you want. For example, particle strong optimization or AI or something like that, or Box-Blanken, or yeah, maybe for proxy. But in here I use the particle strong optimization. And then you select the objective function that have been created earlier. And another interesting function for the objective function, you can set the weighting factor. Maybe at that particular time you see the match is critical at that particular time step, so you can set the weighting factor in there. So this is nice tools. And this is the result of the matching. So there is the objective function in y direction and x axis, and in x-axis there is simulation run. So it's pretty much stabilized after several runs. As I told you earlier, it's really quick, and I get the matching is pretty fast. So maybe I only run like I set the constraint of running 500 times the maximum running, but in here let's say like 50 runs, I already got the stationary point in here. You see and in the right side of this chart, you see the objective function of the X8 and S6 and X8. Since the multiple objective function that we can assess the matching in here is quite interesting tools as well. And this is on the result. So in here it's let me zoom in a little bit. So the data point in here is matched with the simulation. So in this case, with the reasonable match that I get from the X6 and K8, I proceed with the forecasting.
Wow, cool. So how many runs are you done already actually?
Actually, I use the 500 runs of just a constraint, the maximum run that I given instruction to the tNav as okay, the maximum run is 500, no more from that. But in here you see the stationary point can be achieved, let's say like 40 or 50. And you have
so
the
after 50 is already converged, yeah? Is that what you mean?
Yes, the converge. Yep, that's correct.
Because the cross plot, the Pareto plot doesn't look clear. So yes, but I still can see the Pareto plot here. in the red color, right? So, wow, it's amazing. Only runs matching. You're a very good engineer.
No, the tools is great. So I just run through the the workflow. So yeah, so that's the result of the matching. So maybe I proceed with the forecasting. So this is one is the result of the forecast. So let's say the matching has been done with the X6 and X8. But in here, I would like to introduce another case. So what if I would like to proceed of factoring in X7, let's say. So in here, I set up the algorithm for the uncertainty analysis. And for the input from the minimum and maximum, I use the insight from the matching point from the X6 and X8. So in this case, I run the factoring based on what I get from the matching result from the X6 and X8. And this one, the result. And it's pretty much convenient because you see, after you perform the uncertainty analysis, you can automatically create the P90, P50, and P10 model automatically. So you can extract one by one, and you see in each of these models standalone outside the matching function in here. So this one is pretty much important because this one that I proceed to the management that, okay, we have done this from the X6 and X8, and we have the opportunity from the X7, we can get the gain from this in the low case, base case, and high case, let's say. So this one is pretty much helpful for my job in my team.
Okay, so I think that nowadays or recently the probabilistic run is getting more and more popular, right? In the in the simulation industry. So maybe you can give your opinion whether what is the importance of this tool. Or maybe the viewers want to know your opinion about this tool. Is it really recommended or not?
Yeah, I think agree on what you're saying that nowadays the uncertainty analysis is pretty much popular and it's important for the field development plan or program because if you want to proceed and spend a capital, massive capital in a project, you would like to see the uncertainty that you might have. Let's say in this case, we are concerned about the production after we do the stimulation job. So this one is a very great tool. I can propose to the management that, okay, we have the opportunity in our another wells and we have this kind of low case, base case, and high case, and we might have the NPV of the project of this one, and this one. So it's pretty much giving you the flavor of the value increment that you can produce for the particular project, and also taking into account the uncertainty that we might have. So it's pretty much fair for us and to the management that we have this kind of tools. So it's really, really important.
Basically, you mean that this tool will help you a lot in decision making, yeah? Is what you say,
sure,
right?
yes, that's correct. Yep.
Nice, very nice.
All right. Okay, shall we proceed to the
conclusion?
Conclusion.
Yeah, go ahead with the conclusion, then we go for the question and answer session.
Okay, I think this is my last slide. Just want to wrap up the things. So the inputs of the historymesh are the historymesh simulation model and the 1D factoring model from another factoring simulator, which parameter will be taken forward for dynamic model. For the skin factor, like I told you earlier, the equivalent skin that I got is almost -6 on both wells. So it's quite massive negative skin factor in here. That this is quite troublesome for the inputs. And the input from the local grid refinement and grid virtual connection method are directly using the output from the factoring simulator. From the grid virtual connection, it's pretty much straightforward. But from the local grid refinement, you need to create an assumption because this local grid refinement is great tools, but it needs you to put a lot of inputs inside. In my cases, I don't have that kind of more detailed input, so I pursue with the grid virtual connection. So our findings for the running from the above 3 method is the first is the running time for the grid virtual connection is similar with the skin factor method. Meanwhile, the local grid refinement, it takes longer time to finish. That makes sense because you introduce more refined cells in there, so it takes more computational time. But the simulation with the base input shows the grid field connection and the LGR have the similar results, so it can be matched, while the skin factor shows deviation from the two. And the history matching process shows the grid field connection and LGR method could be matched with the actual production data. Meanwhile, the skin factor could not be matched because there's a restriction of maximum negative value that you can introduce in the numerical simulation. So that's probably the case. So based on this analysis, from my case, the grid field connection is a sensible method to model the post-extracting well performance, considering the relative fast computational time and similar result compared to the LGR. So yeah, that's the main takeaway from my study. However, should the detailed factoring inputs are available, let's say, from the factor simulator, I think the local grid refinement is the best method to do this job. I think that tNavigator has also the tools to do that using the stimulator reservoir volume. So maybe if in the future, if I get the more detailed inputs from the SRV LGR, I will pursue with the SRV LGR. But from now on, I proceed with the grid field connection because that's input that I have. So probably that's all from my side.
Thank you, Ricko.
Rizky, do you have any questions?
Actually, I already saw the question box in our toggle, and it looks like there are so many questions already. So maybe we can proceed to the question.
Okay, go ahead.
Okay. So Ricko, so Larissa, can I read the question for Ricko?
Yeah, go ahead.
So Ricko, there is several questions, but I will choose maybe 3 first before we go to another. So the first question is, did you consider the impacts of geomechanical properties, Yau's model for pressure, stress orientation, or sound ratio by using a geomechanical model on the fluid flow in the reservoir?
Oh, I think that's a great question because that's the things that I currently work in. But from this project, the answer is no, because I just simply use the inputs from the fracture simulator, output from the fracture simulator, and as an input from the numerical simulation. So let's say that the line with connectivity of the fracture. But you're right. The geometrical properties such as Young modulus for pressure, stress orientation, and Poisson ratio is important as well. And now we are currently working with that. So we are now doing the 4D geomechanics, and hopefully we can share you the result in the next session.
Okay, thank you. Next question. So what is the reservoir grid size and what is the LGR grid size in your LGR method simulation?
Okay, so the LGR method you can use there's no like you need to do the LGR like particular size, but in my case I use the 10 by 10 refinement from the X and Y axis. So from the Z axis, because it's already thin, so I just leave it as it is. So the refinement that I perform is the X and Y axis 10 by 10. It's teaching the uniform refinement. But you can also use the logarithmic refinement or unstructured refinement to make sure to better capture the physics. But in this case, I use the uniform refinement because I would like to see first the most simplest one of the LGR to make sure that it works.
Okay, actually, in my opinion as well, I think using the logarithmic refinement will be better in terms of runtime because your grid size contrast will not get high when you introduce your LGR in your grid. Also, using the LGR on and off toggle in tNavigator, so it will help you to reduce your runtime as well, because I say that the history match perform for maybe 30 years and the forecast only perform for, the fracture itself only perform for 5 years, right? So maybe using the LGR on and off, it will reduce the simulations, the grid numbers and also the simulation running time. Yeah. Okay. So next question. This is the third question actually. So this is very interesting one. So the question is about fracture parameters and their uncertainty ranges. So where these numbers coming from, and while you want to design the model, and how about the result of forecasting? Is it similar with the actual in the? I mean, forecast means that the proposal is it similar? I don't know whether is it already built or not, but that's the situation.
Okay, so for the model calibration, the basic inputs that I have is only the insight from the fracture simulator in here, from the fracture properties, from length, connectivity, and so on. So that's the main parameter that I input. From the minimum and maximum case, I from the model calibration, I don't have any, let's say, I cannot say any preferences to do that, because it's basically you need to have a range that can actually suits to your data. So basically the main driver. So that's for the existing frac for the calibration. But the 4 future frac from, let's say, the X7 case that I showed you earlier, that will be dictated by the history that I already have in my previous 2 wells, and it can also be added by the analysis from the X7 itself, whether we have a standalone fracture simulator analysis in the X7, we can also use that number. But in here, I use the result from the X6 and the X8 from the ranges that I applied to the X7 from the preliminary simulation run to have the insight.
Thank you. So Larissa, do we still have time?
I think we can have one more question, and let me choose that question as the
sure.
last question, because this is quite interesting. I think the attendee that asked this question is a geologist, so it's from Peter Salisbury. He's asking whether, Ricko, is the field offshore or onshore? Because if it's onshore, I would have chosen prop fractures, because Indonesia is tectonically active areas, and the high lateral stresses might cause premature closure of the acid frac. So that's what his concern is. So what do you think? Where's the field location again?
Okay, I think that's the very nice question. The field location itself in the central Kalimantan, in the middle of Kalimantan forest, is quite remote. It's onshore. It's onshore field. So so yeah, the option to have a prop fracture has been assessed as well. We have a preliminary study whether we proceed with the prop fracture of the acid fracture. But in this case, after we consider all of the things, like the geomechanics and also the solubility of the field, and we run through the decision tree from that has been created by the contractors that perform the job, that's in this kind of the field, that's most suitable to doing the acid fracturing job rather than the prop fracture job. But I agree, that's not eliminate the option for the prop fracture, but we need to look into details into that, because in the fracturing, acid fracturing, we hope that we have the edge that serve as a connectivity, high connectivity conduit from the for the flow to from the reservoir to the wellbore. So that's the main driver why we choose the acid fracturing rather than prop fracturing.
Okay, thank you very much, Ricko. So I think we reached the end of our session.
That's all right.
Yeah.
Although, I mean, we do have an overwhelming amount of questions. That's a good thing. Don't worry, we might not be able to answer them now and today because of the shortage of timing, but fret not, we will answer them personally, and we will email it to you. So other than that, that's the very end of our session. Thank you so much, Ricko. Thank you so much, Rizky. That was very, very insightful. And don't forget to catch our next session next Friday at 2:30 p.m. Kuala Lumpur, Malaysian time, with our next guest speaker from PTTEP Malaysia, Mr. Ronnie Gunarto, as he will share us his insights on the best practices of water flood management. And please note that it's not tomorrow Friday, but it's going to be next week Friday. Yeah. So stay tuned on the same time, right? Yes. 2:30 Cal time. 18th of September, 2020. And all right, have a great week. weekend. Thank you so much, and
Thank you,
see soon.
Ricko.
Thank
Thank you,
you.
Rizky. Thank you, everyone.
Thank you, everyone.
See you
Bye.
again soon.
Bye.
Bye.
Stay safe.
Stay safe.